Hello everyone, welcome to session 2 of the Shimadzu LC Purification series. This series is designed to introduce you to and increase your knowledge of LC purification. This second session in the series looks specifically at semi-micro and analytical scale purification. The Shimadzu LC Purification webinar series consists of 3 sessions. The first covered the fundamentals of LC purification and included the subjects: what is LC purification? How much sample can you expect to purify? Upscaling basics, recycling and concentration. This session is now available on demand through our website. Today's webinar, session 2, will cover the differences between semi-micro and analytical scale purification, principles specific to semi-micro and analytical scales, things to consider at these scales, instrumentation and software advantages. The last session, session 3, titled Semi-Preparative LC Purification, will cover principles, common issues, tips and tricks of semi-preparative chromatography, UFPLC, ultra-fast preparative purification LC, and lastly, semi-preparative SFC scale purification. In session 1, we said preparative LC is concerned with physically separating and isolating an amount of one or a number of components in a sample. That balance needs to be struck between purity, yield, and rate. That flow rates and sample loading can be scaled to different column dimensions. That separation has priority to peak shape. That we should use the weakest solvent possible for large volume injections. That larger particle sizes can be used in preparative LC. And that peak recycling can be used to improve inadequate separations or reduce losses in resolution caused by sample overload. We discussed the range and scope of LC purification overall, but for this webinar, we will concentrate on these 2 levels. So to begin, looking at semi-micro and analytical scale purification. Your goals for purifying your compounds will be as follows. You want to purify them as quickly as possible. You want them to be pure to a level that is acceptable for the next process. You want there to be enough material for that process. You want them to be delivered in concentrated form so that they're ready for the next process. And you want that to be done with a package which is easy to use, reliable, and rugged. We appreciate that your time and samples are precious, so our goal is to help you to deliver your goals. Here we present some solutions showing how LC might be used to deliver your goals. But first, let's define the scales and scopes of these solutions. This will help you in the use of your current systems, hopefully, and your decisions in the future. Semi-micro. These systems have typical loadings of less than 2 milligrams on column. Flow rates vary from 100 to 500 microliters a minute, and column internal diameters vary from 2 to 3 millimeters. Samples are typically biological, proteins in the examples shown. Analytical scale. The loading here is typically 2 to 20 milligrams on column, with flow rates ranging from 1 mil a minute to 5 mils a minute. Column IDs vary from 4.6 to 10 millimeters, and they're used for structural separations. User requirements for these systems may vary, but most will be similar. Most will be dual purpose. Samples are often screened for the presence of the desired components. In these systems, this is often the main use. However, once a component has been identified as a target for purification, the configuration with collector is employed to isolate that compound. At this scale, assays used to confirm the presence of the target are very sensitive, so purity or yield are not the focus. And now to semi-micro scale purification. Semi-micro scale LC purification considerations. As we have just mentioned, these biological compounds are usually not required in large amounts. Low volume collection is typical and involves collection of tens to hundreds of microliters for the smallest peaks. This suits microplates because of their compact low volume, but small tubes or vials can also be used. To help identifying where peaks have been collected, graphical peak tracking accurately displays peak positions in the racks and tubes. Most modern systems will have a visualization of this. Dispersion, excess volume in an LC system. This can cause many issues. In the case of semi-micro purification, too much volume after the detector will cause peaks to be diluted in the tubing. This may result in reduced peak purity. Unfortunately, because this occurs after the detector, it may not be so obvious to the user, but may result in poor purity when it is eventually checked. Fraction collection peak carryover. Removing the last droplet from the tip of the needle might seem minor, but the droplet size can be large relative to the size of the well. So as the collector moves, contamination can be significant if the droplet falls into the next well. Reducing the inner and outer diameter of the probe's tubing creates a smaller droplet, thus reducing the peak carryover. When collecting peak fractions, occasional noise spikes from a detector can cause the fraction collector to start collecting what to the user are clearly not peaks. We can filter out these noise spikes by setting peak sensitivity values in software. This adjustment tunes them out, stops their collection, and makes the process more reliable and predictable. Colored bands on the chromatogram denote which peaks have been collected and where they are located. They will also show a number defining the peak's exact position in the collection rack. Keeping track of mobile phase is easily missed, especially if you're not in the same room or the system's in a cold room. Here, the software will tell you if you have enough for your sequence and where it will stop if you don't. By using balances to weigh the bottles, it constantly checks for their actual content, stopping the system running dry. Modern modular HPLCs have many components. In this case, the system consists of solvents and a balance tray, as mentioned already, a pump to allow accurate isocratic flow, an autosampler to accurately and reproducibly inject your sample, a column oven for routine analytical work if the system is not in a cold room, UV and/or fluorescence detection for sufficient sensitivity. Finally, fraction collector for collecting peaks. Useful software features can be summarized as follows. Mobile phase monitoring, useful if the system is in a cold room, as all functions can be monitored remotely. Automatic peak recognition, making fraction collection easier and consistent. Color-coded peak tracking, this makes identifying peaks post-run easier. User-friendly software for simplifying workflows. In this example, FSEC, fluorescent size exclusion chromatography, is used to show the profiles of membrane transporters A for 4 different species. This and other similar separations are routinely performed on these machines. If needed, peaks are then collected and identified offline. And now to analytical scale purification. The system for analytical scale purification does not differ greatly in design from its semi-micro counterpart. The main differences are few but necessary. Solvents and a tray and balances as before, but now a quaternary pump to allow isocratic or gradient flow is employed. An autosampler, cooled if needed for sample stability, as these systems are typically at room temperature. A column oven for analytical scouting. UV detector with a preparative flow cell. And finally, a fraction collector, but this time with larger tubes. This allows us to meet the increased loading and flow rate requirements for larger columns. Analytical scale purification considerations. First, the emphasis is now about purity, as a specific minimum amount will now be needed after isolation. Dissolving the sample in a concentrated form is needed. This was covered in session 1. If solubility is fine and resolution is good, a loading study can begin and upscaling may follow. Consideration is then given to how to perform collection, whether by peak, by time, or a combination of peak with time slices. The appropriate detection is chosen for the target compound collection. Loading effect. Here we have an example of compound X for purification. It has been dissolved in 50-50 acetonitrile water and sufficient resolution has been gained with the first scout run. As we increase the injection volume, we see more overload as the peak broadens as expected. This happens until we reach a resolution limit with the impurity in front of the main peak still clearly resolved, maintaining our desired high purity. Upscaling. With a 4.6 mm ID column, a 2.5 mg loading on column will give a rate of 7.5 mg per hour, sufficient for NMR identification. If more material is needed, by moving to a 10 mm ID column, we can purify 37.5 mg an hour, which can be used for other processes. Once you have a scale appropriate for the next stage, purification really begins. Fraction collection is key, and collection options need now to be considered carefully. Collecting the peaks can be done in a number of ways. Here are just a few. By peak. If the chromatography is robust and the chromatographic peaks are well resolved, this is a good choice. Detector signals may vary in the units used, for instance AU, RIU, RFU. All of these may be converted into one common scale, millivolts. This is what most fraction collectors use, and the detector chromatogram can be easily reviewed in this scale. If the shown peaks were 100 millivolt high, a reasonable level to start collecting might be 5 millivolts. That would mean if the baseline reached 5 millivolts, the fraction collector would start collecting. It would then stop when the baseline again reached 5 millivolts on the way down. By time. This is useful when you are unsure about what cannot be seen by the detector. Offline tests will determine where and if the desired components are present. This tells the fraction collector then to collect in a time window, for example, starting at 5 minutes and stopping at 10 minutes. Time per tube can then be used to divide into smaller slices. Peak plus time. This is best suited to partially resolved peaks or where there is suspicion of a hidden contaminant. It allows some pure material to be gained at the expense of yield. This is the same peak functions that we used previously of level and slope, but now adds time per tube to subdivide the peaks. To make the process of setting up collection easier, software simulation allows the opening of an optimized analytical run. Click on the peak where you want to start collecting and drag to the point at which you want to stop. The slope values are then stored in the method, ready for running. Compounds can be seen by different detector types, just as with any normal LC. UV, fluorescence, and refractive index are non-destructive, so can be easily connected to a fraction collector. Mass spectrometers and evaporative light scattering detectors are destructive and require splitting. However, at these flow rates, this would involve the loss of significant amounts of compound. Detectors need to be equipped with preparative flow cells to overcome overload and allow optimum fraction collection. This chromatogram shows what happens to the detector signal when a sample is very concentrated. If the peak has an impurity close to the apex, it may not be seen and the peaks will be contaminated. A preparative cell will overcome this. So in summary, we have defined semi-micro and analytical scale purification. Semi-micro considerations. Firstly, resolution is needed more than outright loading. Secondly, low volume collection into microplates or tubes is necessary. Thirdly, there are challenges of low volume collection, namely dispersion, fraction collection peak carryover. Tips and tricks. Peak noise rejection settings should be checked. Fraction tracking, useful for locating fractions, switched on. Mobile phase monitoring, preventing running columns dry. Analytical considerations. Firstly, purity. What level is needed? Secondly, upscaling and how we do this. Thirdly, peak collection modes, time, peak, and peak plus time. Other tips and tricks. We mentioned different detectors and how practical they are for purification. And we also mentioned the need for preparative flow cells. So to conclude, if you are screening biological compounds and require occasional purification for identification, semi-micro purification is the best choice. If, however, you are screening small molecules and require occasional purification of compounds for further use, analytical scale purification is the best choice. You can find us on all the usual social media platforms. Please feel free to contact us should you wish to find out more. That's all from me. We hope you have found these sessions useful. Thank you very much and enjoy the rest of your day.
Excellence in science. Shimadzu.